So, could a computer have an imagination? It sounds like science fiction, right? Well, today we're diving into the brilliant mathematics that actually allow a computer to generate brand new ideas. We're going to break down how an AI can learn not just to see the world, but to create things it has literally never seen before.
I mean, think about it. That's a huge question, right? How do you get a machine to do more than just, analyze or classify data? How do you get it to create something totally new, like generate a face of a person who has never existed, or compose a piece of music it's never heard? Well, believe it or not, the journey to get there actually begins somewhere a little more ordinary. So, to teach a computer how to create, we first got to teach it how to summarize, to compress. And our starting point for this whole thing is a really clever kind of neural network called an autoencoder.
Okay, so picture this. You feed an image, let's call it X, into the system. The first part, the encoder, takes that image and just squishes it. It compresses it down into this tiny, dense representation. We can call it a code. Then a second network, the decoder, has the job of rebuilding the entire original image using only that tiny code. And the key, the absolute genius of this, is that bottleneck, that squeeze in the middle. The network is forced to learn what's truly essential about the image. Otherwise, it'll never make it through that narrow passage.
So, what's the goal here? Well, the entire objective is just to make the output look as much like the input as possible. It's basically a really, really high-tech copy machine. That's it. But here's the cool part. In the process of becoming a perfect copier, it has to learn the most important fundamental features of the data just to get it through that tight squeeze we talked about.
Now, if you're sitting there thinking, hey, this whole idea of compressing data down to its most important parts, that sounds kind of familiar. Well, you're absolutely right. You're onto something. It's actually a lot like a super-powered version of a classic statistical technique called principal component analysis, or PCA for short. Yeah, at its simplest, an autoencoder is pretty much a neural network doing PCA. But, and this is a big but, here's where they become so much more powerful. By adding what we call nonlinearities, basically letting the network learn complex curvy patterns instead of just straight lines, it can suddenly understand these incredibly intricate relationships in the data, stuff that a purely linear method like PCA would just completely miss. Okay, so we've got this awesome tool for compressing and then perfectly reconstructing data. Fantastic. But that brings us right back to the real challenge, doesn't it? Can a machine that's only ever been trained to be a copycat actually create something brand new? I mean, if you just pick a random code from that middle space and feed it to the decoder, what do you get? You get garbage, total junk. See, the network has learned to copy, but it hasn't learned the underlying structure of the data. To get there, we have to make a huge shift in our thinking. We have to move from certainty to probability. This means we have to stop thinking about a simple one-to-one mapping. Instead, we have to start thinking probabilistically. We need to come up with what's called a generative story. The idea is that there are some hidden, unobserved causes, we'll call them latent variables Z, that are responsible for generating the data X that we actually get to see. Here's a really great way to get your head around this. Think of X as the observable symptoms you have, like a fever or a cough, and Z is the hidden cause, the actual disease, like the flu or a cold or something else. Our real goal is to figure out the probability of the disease given the symptoms we see. And in the world of statistics, this has a name. It's called the posterior probability. And the classic tool for figuring this out is something called Bayes' theorem. It connects a few key ideas. You've got the posterior, which we just talked about. What's the chance of the disease given the symptoms? Then you have the likelihood. If you do have the flu, what's the chance you'll have a fever? And finally, there's the prior. Just in general, how common is the flu? Bayes' theorem is the magic formula that shows us how to put all of these pieces together to get the answer we're looking for. But this is where we hit a massive brick wall. The math just breaks down. Because to get our answer, we have to calculate the probability of the symptoms themselves, which means for that fever, we have to consider every single possible disease that could have caused it. In math terms, this means solving something called an integral. And for any kind of complex real-world data, that integral is impossible. You can't solve it. It's what mathematicians call intractable. So, yeah, looks like a dead end. Okay, so the exact calculation is off the table. It's impossible. So what do? We do what smart people have always done when faced with an impossible problem. We get clever. We approximate.
And this is the brilliant breakthrough at the very heart of the variational autoencoder. The core idea here, which is called variational inference, is actually beautiful in its simplicity. It goes like this. If the true answer, that posterior distribution we want, is some crazy, wild, impossibly complex shape that we can't even describe, fine. Let's just pick a much simpler, more manageable shape that we do understand, like a good old bell curve, a Gaussian. And then we just try to morph and stretch it until it's as similar to the true shape as possible. We know we can't find the exact answer, but maybe, just maybe, we can get incredibly close.
Okay, but that immediately brings up the next big question, right? If we're going to try to make our simple shape fit that impossible complex shape, how do we measure how close they are? How do we even know if we're getting warmer or colder? We need some kind of a ruler.
And it turns out we have one. It's a tool from information theory called Divergence. You can literally think of it as a ruler for probability distributions. It measures how different two distributions are from each other. So now our goal becomes crystal clear. We need to tweak our simple distribution, our bell curve, to make that divergence, that distance, as small as we possibly can. All right, let's recap. We have our big idea, approximate the impossible distribution with a simple one. And we have our tool for measuring how well we're doing, Divergence. Now we just need to wrap all of that up into a single mission, a single objective that we can actually hand over to a neural network and tell it, go learn this. And this brings us to the absolute heart of the VAE. Now, through some really clever mathematical gymnastics, it turns out that minimizing that divergence we talked about is mathematically the exact same thing as maximizing a different value, something called the evidence lower bound, or ELB. Look, don't get hung up on the symbols or the name. The intuition is what's important here. This one formula contains the entire mission for our network. And what's so cool is that this one, kind of complex-looking formula actually breaks down into two beautifully simple and sometimes competing jobs. Job number one is reconstruction. This is familiar, right? Just like our basic autoencoder, it has to get really good at copying the input. But then there's job number two, regularization. It has to keep all those codes in that middle latent space, neat and organized, forcing them to look like a simple, standard bell curve. It's this constant tug of war, be a perfect copycat versus stay organized. And this whole idea leads to a really crucial change in the network's design. A standard autoencoder, remember, encodes an input to a single, precise point. A VA is different. Its encoder maps an input to a whole probability distribution. It spits out a mean and a variance. So it's not saying the code for this image is right here. It's saying, well, the code is probably somewhere around here in this fuzzy region. And that little bit of probabilistic wiggle room, that is the secret sauce. So let's step back. We've gone through all this trouble. We've forced our network to do two things at once: perfectly reconstruct the data and organize all its internal codes into this smooth, predictable probabilistic map. So why? Why did we do all of that? Well, it's all for the payoff. And it is magical. The results of this two-part mission is just amazing. That latent space, that code spaced in the middle, it's no longer just a messy jumble of disconnected points. It has become a smooth, continuous map of concepts. Points that are close together on this map correspond to images that are similar in the real world. You can literally start at a point that represents a smiling face, move just a tiny bit on the map, and you might get a face that's smiling just a little bit less. It's all connected. And now for the magic trick. This is the whole point. Once the network is fully trained, we can take the entire encoder and just throw it away. We don't need it anymore. What we're left with is this beautiful, organized map and a decoder that knows how to read it. So now we can just pick a random point from that simple bell curve we forced it to learn, feed those coordinates to our decoder, and poof, it will generate a brand new, totally realistic piece of data it's never seen before. The decoder has learned to turn abstract map coordinates into concrete reality. It has become a true generative model. So think about where we started. We began with a simple copy machine. But by forcing it to do more than just copy, by forcing it to organize its internal knowledge into a meaningful, smooth map, we gave it the power to create. We, in a very real sense, taught it how to imagine. And it really makes you wonder, doesn't it? If we can teach a machine to generate new images, what kind of new ideas could it learn to generate next?